I'm going to come on now to discuss the distribution properties of the Wiener process in some detail, beginning with the univariate slice distribution, which is the distribution of the process at time t. And as we saw earlier, that's simply a normal distribution with parameters mean mu t and standard deviation sigma root t. Let's look at a Wiener process with parameters 0.25 and 1. So mean of 0.25 and standard deviation of 1. And we want to look at how that process evolves through time from t equals 0 to 4. And I'm going to plot that distribution over the range -4 to +4. And as you can see, as we move through time, the variance in the process increases, and the mean of the process moves to the right, becomes more positive over time. We can compute the probability density function for a Wiener process with parameters mu and sigma. And that's simply the Gaussian distribution with parameters mean mu t and variance t sigma squared. If x follows a Wiener process with parameters mu and sigma, we can calculate, for example, the mean of a function of x, say x squared, quite simply. In this case, it's t times t mu squared plus sigma squared. Likewise, we can easily calculate the probability of an event. So again, if x is a Wiener process with parameters mu and sigma, then the probability that at time t, x will exceed the value 5 is given by this expression, 1/2 of the complementary error function of 5 minus t times mu divided by square root of 2t times sigma. The complementary error function is merely a convenient way of describing the CDF of the normal distribution. Moving on, we can, for example, calculate the time a Wiener process takes to achieve a certain specified level. Let's look at an example. Here I'm considering a Wiener process with mean 1, standard deviation 1, and I'm looking at the process as it evolves over t equals 0 to t equals 15. And I'm going to look at 10,000 sample paths from that process and the times taken to exceed the level 2. Let me generate that data. And then we'll look at the distribution of the times, which we can estimate to be from an inverse Gaussian distribution with location parameter just over 2 and scale parameter equal to 4.34. And if we plot that distribution, you can see there's a very good fit between the empirical distribution and the theoretical distribution. We might want to estimate the time to achieve the maximum value over a certain time interval. In this example, I'm considering a Wiener process with mean 0, standard deviation 1, and I'm looking at that process over a time interval from 0 to 1. And I'm calculating the time at which the maximum value is attained in that time interval. I'll take 10,000 sample paths as before, and then I'll extract the times at which the maximum value is attained in each of those sample paths. And we'll plot a histogram of them. When we do that, we find that the empirical distribution follows an arcsine distribution, as shown here. There's a large probability that the maximum value will be achieved at time t equals 0. What does that mean? It means that the process moves immediately into negative territory and stays there throughout the time interval from 0 to 1. So the maximum value is attained at time t equals 0, the initial value of the process. There's also a large probability that the process will achieve its maximum value at t equals 1. In those instances, the process will move into positive territory immediately and evolve in the positive direction continuously over the unit time interval. And then, of course, there are lower probabilities that the maximum value will be achieved somewhere between the range 0 and 1.